we have some population data here for Billings, and we want to write the exponential growth or decay model. Now, it does look like it's growing, so that's the first thing we can recognize is that we're going to have a b value that's bigger than 1 because in 2000 it was smaller than it is in 2020. So this is usually how scientists get their data. It's very rare that you just say like, oh, this is a growth rate, and here you just hand some perfect data and calculate that. That's not how it happens. Most of the time, scientists have to look at something, measure it one time, then they have to watch it grow, measure it a second time or a third or a fourth, and watch for a pattern. And so that's what we're doing here. Now we're just going to assume that it's growing exponentially because population usually does grow exponentially. If you look at the graph, sometimes it doesn't always grow perfectly exponentially, but we're just going to make that assumption on this one. So pretend that decimal place there is a comma because that's a little typo, but all right, so we have this data and we want to figure out what the exponential growth or decay model is for Billings. So let's just call 2000 our initial year, okay? And it doesn't truly matter what year we choose as the initial year because if you think about it, every year we're multiplying by the same number, right? So in 2000, say we were doubling every year, which we're not in population, but say we were doubling. I would take the population in 2000 and I would multiply it by 2. And then I'd take the population in 2001 and I multiply it by 2. Okay, so it truly doesn't matter where I start initially because every year I'm still multiplying by the same number. So whatever my initial value is, if I took my population at 2005, multiplied it by 2 every year, I would still end up at the same population for 2020 as if I took the population in 2000, multiplied it by 2 every year from 2000. Does that make sense? So it doesn't matter which one is your initial. Like if 2000 is not the absolute 0, obviously this is not the first time Billings ever had people in it, but we're just going to call this our initial amount. So we're going to write our exponential function and we have y equals a times b to the x. Okay, so what do we know? We know the initial amount, so we can say y equals 89,887, and we don't know the growth rate to the x, okay? But now we have 3 variables instead of 4, so that's helpful. Now we need to get rid of some more variables though, right? Because we need to find that b. We do know that in 2020, the population was 109,550. So that means there's a point on this curve when x equals 20 in 20 years that our y equals 109,550, right? That's a point on our exponential function. So we can just plug that in to our function and solve for b. So we know that in, oops, I did that wrong. Let's see, in that y is going to equal 109,550. I'm going to try to stop saying that because every time I say it, I stumble over it and it's just going to confuse you. So it's, you know, that number. Okay, b to the 20th. All right, so let's solve for b here. So we're going to divide both sides by 89887. Okay, and so then here we have this 109, I'm not even going to say it, see, because I'm just going to stumble over it. 89887 equals b to the 20th. And how do I undo an exponential? Well, I raise this whole power to the 1/20th, right? Which is like taking the 20th root of something, but it's so much easier, especially in your calculator, to just do to the 1/20th. Now, if I multiply 20 by 1/20th, that's going to just give me b on this side. And then on this side, I have this whole mess, okay? So now we're going to go ahead and put this into our calculators. So while I'm writing this ridiculous thing out, go ahead and get your calculator ready. And let's take a look. Okay, so here we are. We're going to say, we're going to make sure to put parentheses around this. And I'm going to go 109,550 divided by 89887. And I'm going to close parentheses. I'm going to raise this. Instead of using, in the math menu, you can find the 20th root by, you know, doing the xth root. But it's so much easier just to do this. 1 divided by 20, right? You just raise it to this power with the caret to the 1/20th. Enter. And we get 1.009940. Okay, I'm going to write this down so we can 1.00994. 0468. Now, if we were going to use this in another calculation, like if it said how many people are there going to be in 2050, let's go ahead and store it. So you can push store, and it's going to store whatever the last number was. And then we're going to click alpha, and I'm going to pick B just so that I remember where it's at, and I'm going to push enter. And now anytime I use alpha B, it's going to bring back up that number that I wanted. Okay, so this is our number that we came up with. So what does this mean? What does this actually mean? That means that every year the population of Billings is getting multiplied by 1.00994, whatever. Okay, so that's about 100.9%. It's about 100.9, excuse me, 100, not 109, 100.99%. So it's growing by almost 101% every year. So we could write our exponential function now that we know our b. We could write y equals, now our initial value was 89887, and our b is 1.00994, and then I'm just going to put some dots to the x. And like I said right here, we can just plug in a new value. So if I wanted to go back to my calculator, I could say, okay, what would the population be? Let's see, this started in 2000. Yeah, let's do it in 2050. So 50 years after. Then we take that b to that power, multiply it by our initial amount. And that's going to be the estimated population of Billings. So it's really curious. I'm super curious to see in 2050, come back to this video and see if that's our actual population.